Okay, sorry for being here again. I was as disappointed as you. I thought I was done on Monday with the talks and everything, but then I had to do this. So we report a bit of the discussion that we had within the massive black hole binary group, which was basically the discussion was led by Monica, Neil, Sean, myself, and there were about 15, 20 people. So I keep saying the name of the people that were there because I don't have much to say otherwise. So we got a list of questions which look like this. So this is page 1, page 2, page 3, page 4, page 5. So there was no way to try to answer all the questions, and what we did was to basically identify general topics that would have been interesting to address or to tackle from the new ELISA perspective. So in particular, we talk about how do we assess basically the early massive black hole evolution with ELISA. Is it important to measure spins and eccentricity and what we can get from those spins and eccentricity? And also importantly from the waveform modeling and data analysis point of view, what do we need in order to get a parameter accuracy which would allow us to get the astrophysical and the fundamental physics information that we want. Last but not least, I will talk a bit about doing fundamental physics with massive black hole binaries. And I will tell you why we thought this can be interesting and important to address with this new design of ELISA. So when we talk about ELISA, so we realize that light binaries are particularly interesting because, well, for the simple reason that light binaries are the binaries for which we have less information. So we see binaries of 10 to the 6 solar masses and up, okay, in the local universe, and also at high redshift are treating as quasars, but we don't have information on light massive black holes. Sorry, so we see binary. I wanted to say we see black holes. And we don't have information about light massive black holes, sorry for the oxymoron, neither at high redshift or in the local universe, because these are simply too faint to observe, okay? So in particular, it would be interesting to assess the massive black hole formation mechanism and to assess what is the low mass end of the black hole mass function, okay? In particular, there are observations suggesting that when you go toward low mass galaxy, okay, or dwarf galaxies, this central massive black hole may be replaced by the compact stellar cluster, okay? Is the massive black hole coexisting with the star cluster, or there is a transition? What is the occupation fraction of light black holes in these dwarf galaxies? So this may be this would be maybe an important thing to people going off and online on my Skype, okay? Don't send me messages, please. And this is, well, actually, this is also an important thing, probably most also for MRIs, okay? Because with MRIs, you can probe the dynamics of these dense nuclei and to see if there are black holes in here. What do we need to do for this? First of all, we need a systematic exploration of what we call the inverse problem. Well, inverse problem with respect to the usual thing that is done when you start to do prediction for a new field. You start with a model and you say, okay, this instrument will see 100 events. And the inverse model is that the inverse problem is, okay, you see 100 events, what can you say about the underlying model, okay? This is the work that I also presented a bit on Monday. One fundamental thing to do would be to address this problem in a full, let's say, parametric context. Because what you want really to know is for example, what is the mass function of these seeds? What is the redshift distribution? We don't know if they form at redshift 30 or at redshift 10. Okay? What is the efficiency of accretion? Yes, thanks. Wait second. So if you want to be friends with me. Okay, what is the accretion efficiency of these seeds? But these parameters may well be degenerate when it comes to the observation of coalescing binaries, and we don't have a mapping of how these parameters translate into the population of the massive black hole binary you may see. So a full parametric study of this problem would be very valuable to assess really what we can say astrophysically about massive black hole binaries. So this brings me to, okay, we want to measure these massive black hole binaries, and we want to measure, we have to measure their parameters. So this is one, you already see this plot. This is from a study that we are doing for ELISA. So one of the things that we realized going to this, from classic ELISA to this new design, is that now we really need to exploit all the waveform features to get useful information about your sources. So if with classic ELISA you could get along quite well just with the spiral, and to see, okay, I can measure the mass pretty well and sky position pretty well, pretty reasonably well with the spiral. Now you have to use full waveform with the spiral merger ring down, spin precession, higher harmonics, eccentricity, whatever. This is what we start doing, but still most of the studies estimate the errors with the Fisher information metrics, which may be inappropriate for in many cases, especially when the error is large. Sorry?
Are we allowed to make comments?
Yes. The other, yes, you are.
No, we say this every year. This is kind of looking at it backwards. So it's not that you need to exploit all the waveform features, because the features are there.
Yes.
So if you were to analyze data without them,
yes,
you probably get everything wrong, the mass
okay,
and so on. So if what it is that we were just doing a simplified problem, we thought we were happy already with what we got, but we would always have had to do that.
Oh, yeah, sure.
With the real ELISA, the complexity, you can turn it off, right?
Right. Thanks for the clarification. sorry. And so, for example, one example is the luminosity distance. The error on the luminosity distance usually we say is 100%, right? But okay, we can't use the Fisher metric approximation for a 100% error, right? And that error is not 100% because you know the redshifted mass, and you know that source is not basically in the galactic center. You know it must be at least at some redshift. Okay, so we need to properly use the information that is enclosed in the likelihood, and so we need to really do the full problem with the Markov chain or whatever technique it is to assess what we can do. So what accuracy is needed actually for astrophysics? So I would say that for most of the astrophysical purposes, every intrinsic mass measurement at 20% level would be great. Okay, and I'm talking about intrinsic. Okay, the redshifted mass, we know that we can measure it pretty well, because apart from the galactic center, maybe there's no basically. Maybe a couple of measures. There's no other way to determine a mass of a black hole with this precision. The spins, well, people claim that K measure spin with K alpha emission line at a few percent level, and they do so in some studies, but it's also true that few percent is the statistical error without considering the systematics. The systematics given by the fact that the models, the value that you get is often heavily dependent on the model that you're using. And there are several measurements of the spin of the same black hole using the same iron line feature from two different groups that give two inconsistent values of the spin. But For inconsistent, I mean, you know, higher than 0.9 and lower than 0.4. So claiming that you can do it at this point with X-ray astronomy is actually, you know, is simply not true. Okay, and so any measurement done with gravitational wave would be much cleaner and would be taken more seriously. So this is an important thing, exploiting the spinning. Of course, if you could, in principle, go to a 0.1% precision, this would be great to probe maximal massive black hole spins. So what is the maximum spin that the black hole can reach? It's 0.93, 0.97, 0.998. And this will give you insight on the accretion physics and on what's happening in the last stable orbit, okay? And stuff like this. The measure of the distance, that's an interesting point because it's strictly not quite necessary, at least for the study that we did so far, for model selection. In the sense that usually these models are distinguishable using reshifted mass ratio, and spin. However, working on this parameter is important to get excitement into the astrophysical community. Because it's important if you measure an object at a high redshift to be able to say that that object is at high redshift. Okay. So it's much more exciting to say that you found a massive black hole binary coalescing at redshift 12 than to see I saw a massive black hole binary coalescing at redshift consistent with 12, but maybe also 2. Okay. And scale localization, and if we can achieve some scale localization better than 1 degree or so and a distance better than a few percent, these probably are sort of minimal requirement for having a chance to get a counterpart to this event and to do all the fantastic physics that you can imagine with that, and maybe in principle possibility to do cosmology. So in order to achieve that, we had this fantastic idea to put 2 interferometers in space, for example. That was just a joke, but the Chinese ALIA, or how it's called, so it's supposed to be a LISA-like interferometer. If they fly it at the same time or with some overlap and they put it in front of the Earth instead of behind, then you have a much larger baseline. And you can get a perfect sky localization basically of the source. So that would be just a crazy thought. But
it's high frequency.
No, it's the sensitivity curve at low frequency is basically the same as this.
Yes.
Yeah. So just in case. So one interesting thing that you can gain by measuring massive black hole binaries is to get parameters of massive black hole binaries, is to get insights on their dynamics. So, for example, we can get information about eccentricity. So, we know now, we expect both stars and gas to increase the eccentricity of the systems. But the distribution of coalescence may be quite different. And so here is just a plot with different distribution of, let's say, this different eccentricity distribution in the LISA band for different population of black holes that merge according to different sinking processes. So these binaries usually are quite eccentric in the LISA band. This is actually not the LISA band; it's a bit lower frequency, but not as quite. Most of the time they're going to be 0.1 or so. So what we need to be able to detect this eccentricity, and at 10 to the minus 3 level accuracy is probably what you need to pick most of the systems. So you don't need to go to 10 to the minus 5, 10 to the minus 6. In general, these processes they don't produce extremely eccentric binaries. So the detection of an extreme eccentric binary at the LISA band would be probably a smoking gun of some exotic process for the coalescence of this thing, like triple dynamics. In general, if you have a triplet, you excite the eccentricity of the inner binary, and you can get eccentricities in the LISA band, which is close to 0.5 or higher. Okay. And this is something that you don't get in general with the other mechanisms. So looking into eccentricity can help us to get something about the dynamics, but the most important thing can actually be spins, because we have models now for how the spin behaves according to different models of accretion and merger for these massive black holes. Particularly, you already heard about the dry and wet coalescences. So if the spins are aligned or not, this may be a smoking gun of what is the driving mechanism of this binary. And we need, of course, to model much better to get a better insight of these dynamical models in order to map again, because this is the real issue here. The real issue here is mapping the models that you have in observables. Okay, and we are not quite there yet. Okay, we can't just say, well, we can of course say, okay, wet mergers, spin are aligned, dry mergers, spin are not aligned, but this is a sort of simplistic statement, okay? But maybe spins will help us to do so, and also to distinguish between the typical massive black hole accretion channels, because you expect in general high or low spin depending on what is the channel of accretion of the black hole. So measuring the spins is one of the most important features, I would say. It's one of the most important goals of this mission, because there is not as much information in the other things that we can measure as there is in the spins. So that's probably my personal opinion, but that's all I feel like saying it. So this is what we wanted to say about astrophysics, what we need to do for maximize the astrophysics with this instrument. And then there is also, we thought also a bit about doing fundamental physics. And the motivation for this was the following. So here, you saw this table already from Jonathan. So you have some rates of Emery spirals for LISA and the configuration of the scope. So you see that for LISA you would expect probably several hundreds of this system. But already with the scoped version of the instrument, for example, configuration 2, 1 Michelson, which is what we may have, what we will have probably, you see you go around 50 or so, okay? So you get a loss by a factor of 10 because basically your sensitivity curve is just not as good as before, okay? So you have 500, you lose a factor of 10, you get 50, which is still good, but then you didn't take into account for the tal factor. So tal factor tells you that the Emery rate can be a factor 10 to 50 less, not loss. No, factor loss of a factor 10 to 50. A factor 10 to 50 less because of this, for example, for this barrier that we were talking about, right? So this is just a joke to say that we don't have quite an handle of what is the intrinsic rate of these Emerys, okay? So with the scoped sensitivity curve, with some new process that came out and whatever, we may well end up with no Emerys. So now I don't want the Emery group to be angry at me, but just consider this possibility. If you end up with no Emery, so what kind of what can you do fundamental physics with massive black hole binaries? So are massive black hole binaries good for to do something? So there were already a lot of work actually in this field. So here, this is a picture from Berti et al. Picking on the original idea of Sam and collaborators. So in principle, for example, what you can do, you can test the Noether theorem if you measure three ring down modes of the ringing remnant. Okay, because you need. So if the black hole is scared, you just have spin and mass, okay, as parameters. And if you measure three modes, you can prove that you just have these two parameters, okay? So the point here, so how good are these massive black hole binaries to test GR and fundamental physics? So can you test the Noether theorem? So here I'm not the expert of the group, so you can, if I'm saying something incorrect, you can stop me. But what I picked from the discussion is that it's actually not quite clear if we can do it, because you need ISNR in each mode, but you also need to be able to disentangle each mode from the others. And as far as I understood from the discussion especially between Nico and Neil and Satya, is that it's not clear if you can do this, if you can do so. And one of the things that would be interesting for as a future direction of research is to actually look properly into this problem, because if now memories are maybe in danger, so it would be worth to see what kind of fundamental physics we can do with massive black hole alone. And as far as I understood, we don't have an handle on that yet. So what can you test alternative theories of GR? Well, maybe theory involving massive graviton and tensor scalar theory, you can do it. But theory involving quadratic correction of the curvature is probably, massive black holes are probably not good, because this correction usually goes with a stronger for system with a larger curvature, which are the less massive system. Okay, so with stellar mass black hole is much better in this case. One problem for comparing general relativity with these other theories, supposing that we have perfect waveform for general relativity, is that we lack waveforms for the other theories. And for example, we don't have a proper waveform for a massive graviton theory involving merger ring and whatever. And nobody, as far as understood, wants to try to do this numerically. Okay, because you say, okay, I guess the way the numerical relativists think is we have a lot of things to do in general relativity, so before looking at this. But we can always do a null test, just saying, okay, we have our waveform, and we see what is the residual of the waveform, and we can see at what level we can prove general relativity. Yes?
I think that actually the correct statement.
Yeah. I mean, I may be incorrect in this because it's.
I think it's completely wrong.
Okay.
I think the correct statement is that no numerical relativity person in his right mind will say anything about how they want to attack this before they publish the paper.
Sorry, can you say it again?
I think that no numerical person in their right mind is not going to tell you anything about how they want to approach this problem before they have published the paper, but there's certainly people are thinking about it. Of course.
Okay.
It doesn't
No.
other than
Sasha, if you speak that way, over here we can't hear you.
that's fine.
You're a microphone. You have a microphone, Monica.
So he's writing a secret paper.
No, absolutely not writing it. I'm certainly not writing a secret paper, but if I see a paper on the archive tomorrow that addresses this problem, I will not be surprised. But
there has been at least one paper already. Nico Eunice, about a year ago.
No, but we're talking numerical.
no, we're talking about full numerical relativity.
We're talking about numerical relativity here. So.
I think that, so I was in this session, were you? So I think the statement is that there are no numerical relativity merger waveforms or results for alternatives of gravity.
Right.
Yeah,
That's what I'm saying.
No, it's not true. Either.
It's not true?
Well, there are plenty of theories that there are quadratic theories if you look at that. They have higher clearances.
Nico, all the waveforms that we have are also valid for Nasdaq.
What?
All waveforms that we have are valid for Nasdaq, for instance. Nasdaq are going to be kept, and for black holes, the effect on the relativity is not there. So.
Yeah, so we're thinking about things that could actually change the waveforms, not things that wouldn't.
I think that's clear.
No, but I mean, the way you have to distinguish the theory in this case.
Nothing. You can't say anything.
Okay, in any case, the bottom line is that
Stay tuned for the next year.
it may be interesting to look more into this, how you can do for fundamental physics with massive black hole binaries at this point. So before leaving, I want to pick a second on a question that we actually didn't tackle properly, which is the connection between communities. So we have we will probably maybe have LISA. We have pulsar timing, and there is and these two means of probing gravitational wave are completely orthogonal because you probe different parameter space of the population. Here you have the inspiraling massive black holes that you see with LISA. Here you have your population of massive black hole binaries that you may be able to observe with pulsar timing. And this thing looks very similar in how the signal is built up to what would be the white dwarf binary confusion noises in LISA. So we have a quite large community that have looked into this problem already and that is working this problem, and it would be very, very fruitful to jump from one problem to the other and try to apply these techniques also for the pulsar timing case. That would be very important for try to get a detection of these gravitational waves. That's all.